Okay. Thank you, Siddharth. Let me first thank the organizers uh, for inviting me to give these lectures. So I am supposed to talk about the QGP theory part of this school, and so what I have thought that I will first, in this first lecture, so there are 4 lectures, 45 minutes each. What I have decided is in the first lecture, we will basically go through the
Recording in
uh,
progress.
QCD thermodynamics uh, till date, whatever knowledge we have managed to gather through various explorations. So at the start of the lecture, let me also announce, I think the organizers have already announced that there is this provision of 3 best students will be selected and probably rewarded. So for that, what I am going to do is there will be a few questions which I will flash in the slides themselves. And so those will be like homework assignment. And so evaluation, for my course, I will evaluate based on the response in those questions. And in addition to that, uh, people will be rewarded based on the questions they ask during this online mode school. For my course, at least, that's how I have planned. So this is just an invitation for you to unmute and raise a query whenever possible. So I don't have many slides, maybe just 12 or 14 slides, and expecting that you will be very vocal and you will try to object to many things that we are going to discuss, or at least you'll have the spirit to discuss. Okay, so please feel free to stop me whenever, and just ask a question, and we will be happy to take and discuss. Uh, yeah. Okay. So today, as I said, we will be focusing on the QCD thermodynamics. And so when I say QCD thermodynamics, maybe I should or say like it's the uh, equilibrium properties, equilibrium QCD properties, which I am trying to refer to, right? Because the word equilibrium is very significant, because our school is with the reference, we are keeping in mind that we are going to study QCD medium in a heavy ion collision experiment, right? So there now, what is equilibrium and what is out of equilibrium is a big question, and hence I want to emphasize on this. So first, we are going to focus on the equilibrium properties, and then we will, in the forthcoming lectures, we will try to see how these established equilibrium properties can be extended and can help us or guide us to study the matter which may be not in complete equilibrium, okay, uh, but some sort of equilibrium one could define, and then the frameworks that one develop within equilibrium QCD properties, they could be carried forward and used in studying even matter which is slightly out of equilibrium or out of equilibrium, right? So but today's discussion is completely on sorry. Okay, I think this one got lost. There was some. Okay, so yeah, so complete equilibrium properties, and in that first we are going to look at lattice QCD approach, which is a first principle approach. First principle method to study QCD equilibrium properties in the thermodynamic conditions which are accessible to in heavy ion collision, where the medium is non-perturbative, and hence lattice QCD is our currently it's the best framework that we have to study, to probe the equilibrium properties of this medium. And then the QCD medium at various limits, how we can consider the QCD medium to be simply a non-interacting gas of quarks and gluons, and in some other limit we can also consider them to be just a simple non-interacting gas of hadrons. Okay, so these are various limits of the QCD medium, and so those we will look at. And then finally, having established or having understood these things, we will come to the QCD phase diagram, which is our main goal to study. To study heavy ion collisions, right? We want to unravel the structure of the QCD phase diagram, and so finally we will come there. Okay, so let's get going. So the QCD thermodynamics. Yeah. So so this is the QCD Lagrangian. I don't want to spend much time in the QCD Lagrangian because I think this is going to be covered by Sayantan in his lectures on the standard model, where QCD is, of course, one part of the standard model. I just want to highlight that we have the QCD Lagrangian has several components. So one is, of course, coming from the gluons, the gauge fields, right? And this other so the F mu A, these have been expanded here, where these are the gauge fields, and these are basically the signatures of the fact that this is a non-abelian gauge group. And so FABCs are the structure constants that come up in the appropriate representation of this SU3 group. And then, of course, we have the matter fields, which are your quarks and antiquarks. And there is a simple kinetic term here, right? And of course, here is the coupling term, coupling with the gluons, right? And this is the mass term for the quarks, right? So I'm sure Sayantan will go into more details in this. So what is important over here is this statement for our course, that for conditions accessible in heavy ion collisions, right, the QCD coupling is large, right? And the QCD coupling is sitting here, which is this G, right? That's our QCD coupling. So that is large. So hence, in your standard quantum field theory course, you must have studied how, if you have such a Lagrangian, how to evaluate via Feynman diagram methods perturbatively various processes, right? And then you do them up to some order of G, right? In either a tree level diagram or a loop level diagram, or you put in corrections. But that is done with the picture in mind that this coupling is sufficiently small that such a series converges and makes sense, right? Order by order. But I mean, that is good when you are studying QAD, but unfortunately for QCD, and particularly in the regime where we want to study QCD, okay, there the QCD coupling is large. And hence, the standard perturbative methods, which you might have studied in your quantum field theory course, quantum field theory 1 course, okay, will fail badly. And that's why one needs non-perturbative methods, and lattice QCD is one of the, at the foremost uh, in amongst all the various candidates that we have right now to study field theory in the non-perturbative regime. Okay, so the lattice QCD approach, let's just a few slides to introduce ourselves to what is going on in the lattice QCD approach, because very often you will come across results where lattice results, and we should not get lost what they're saying. So we should learn how to infer the important things that we want to know, which will become useful in our understanding of avian collision. So keeping that in mind, so basically in the lattice QCD, what you're doing, it's basically a direct determination of equilibrium properties of QCD medium, right? By numerically evaluating the QCD path integrals, right? So the starting point is, of course, the same vacuum to vacuum transition amplitude, okay, in a Feynman path integral formulation, which is this. And this is standard expression which you must have come across in your quantum field theory 1 course, for example, right? So what is being done here? This is the QCD Lagrangian, which we had already seen here, right? And because this is a path integral approach, here the gluon fields and the fermion antifermion fields, these are all taken as classical fields, right? These are all classical fields. So then you could ask, then how do we get back the, how do we take care of the quantum nature? Well, the quantum nature is taken care of by doing this integral, right? By basically doing this integral over all possible configurations of these fields, right? The gluon field and the matter fields. However, comparing to a classical approach, what you do usually is from this Lagrangian, you basically solve the Euler-Lagrange equation of motion, right? And that equation of motion gives you picks out one particular configuration of these fields, right? And that's the classical configuration. That's the classical approach. In the quantum approach, what you are doing, you are not only taking care of the classical configurations, right? You are also taking care of the all other possible configurations, right? So of course, each configuration is being taken into account, but there is a weight factor that you are associating, right? This is the weight factor, which is the famous Feynman's proposal of e to the power I and action, right? This integral d4xl is nothing but the action. So that's the standard Feynman's proposal to basically convert the whole quantum field theory problem in the language of operators into basically just classical fields, but now you sum over all configurations and not giving equal weightage to all configuration. Classical fields might get more weightage depending on how this action evaluates, and then however other fields are also being included, right? So the partition function, now this is the vacuum to vacuum transition amplitude, and from here the partition function can be also obtained. There is a standard recipe for that. So the partition function, and in a grand canonical ensemble, right? So of these quarks, antiquarks, and gluons in thermal equilibrium is basically simply obtained by here you will have, for example, the time direction, right? And that is being replaced by this imaginary tau, where now tau varies from 0 to beta, and in this beta is hidden the temperature of the medium. Okay, so where T is the temperature of the system.
Excuse me, sir.
And yeah.
Yes, so sir, what do we
Can
mean
you
by?
please tell your name first?
Yes, sir. I'm Rakesh, sir. Rakesh Naik.
Okay.
Okay.
Yeah,
So
please go ahead.
what do we mean by all configuration here? I didn't get that properly.
Okay. So what we mean by all configurations here is the following. Um, so let me, for example, take this psi of x, right? So here by x, we actually mean, I mean, 3+1 direct dimensions, right? So there is our standard, I mean, x, y, z, and t, right? The space time, right?
Yes.
3+1 space time. So um, that is what this x refers to. Now, right? Now, this psi of x, when I'm saying, right, this is just a classical field, right? For example, I mean, if you think, oh, fermion field, if this creates a problem in your head, you can just think any field, say density field, right? That's a scalar field, okay?
Yes, sir.
But this one has different transformation property under Lorentz group, so that's the complication. But otherwise, all that it means is that you supply a space-time point, right? You supply a space-time point, and it gives you back a value, right? Psi of t, x, y, z, right? That's some value, complex value here, for example.
Yes.
Right?
Yes.
So by configuration, all that it means is you can now think that at every t, x, y, z, there is a value of psi, right? Okay. Now,
Okay.
so now you collect that set, okay? Psi,
Yes.
psi at t1, x1, y1, z1, okay? Then
So we are
psi,
considering all those points which are possible, and we are taking care of
yeah.
all
So
points.
just a second. So I do
Okay.
this, right? And imagine that this t, x, y, z is basically varying over all space-time points, right? Okay.
Yes, sir.
Hello. Yeah.
Yes, sir.
So then this set is actually one configuration,
Okay.
right? Because here you are talking of the field itself, right? So this
Yes.
one set is one realization of this field, right? So one
Yes.
functional dependence, right? There, then here the next configuration, right? Second configuration, again in those same points, right? Here you could change it slightly, right? Here you could change it slightly, and then you get a different profile, right? You get a different function, right?
Yes. Yes.
So each configuration is like one function, right? In this x, y, z,
Okay.
t space. So
Okay.
that's why these integrals are called functional integrals, right? It's an integration over function in the function space. Okay.
Yes, sir. Yes, sir.
So I
Yes.
hope it makes a little clear.
Yes, sir. Yes, sir. It is fine now. Thank you, sir.
Okay. Okay. Great. Good question. Okay. So let's carry on then. And you see, out of all these configurations, Euler-Lagrange equation of motion would have picked out one particular configuration, right? That would satisfy the Euler-Lagrange equation of motion, right?
Yes,
So
sir.
that when you do that, that means you are just working within the classical regime, in the classical framework. And then you are doing quantum mechanics of fields means you are basically also taking into account other configurations, right? With some weight factor. Okay, weighted by this e to the power is. Okay,
Yes, sir.
so
Yes.
right. so that's the vacuum to vacuum transition amplitude. And from here, basically one can get the partition function. This is a remarkable result. Okay, we are not going to get into it, but I am here just telling you the prescription. Of course, people who are interested, this is a standard prescription, and any standard textbook you will get I mean the proof and so on. But so just at every time the time you are replacing by this imaginary tau, where this tau is varying from 0 to beta, and this beta is 1 by t, this is how the temperature enters this ensemble averaging. Okay, and further, for consistency, one also has to make these gluon fields, they should be periodic. Okay, uh, periodic in tau, right? So that means the value at tau equal to 0 should be same as the value at tau equal to beta for the gluon fields. However, for the fermion fields, okay, it's the opposite. It should be anti-periodic. So the value at 0 and the value at beta, they should be related by a negative sign. Okay. So these constraints come, if you go deeper, you'll see why, because of the fact that one is a bosonic thing and the other is a fermionic thing, right? So those are details, but it is just good for you to know them as information. Okay, so now that you have the partition function, okay, so then of a grand canonical ensemble, then your statistical mechanics course tells you everything that you need to know. I mean, you can now know everything that you need to know because you know the partition function of this statistical ensemble, right? So that is indeed what is done. So path integral now for the thermal equilibrium ensemble average, right? So by these angular brackets, right? These angular brackets, we actually mean this thing, right? Equilibrium ensemble average. So which is being defined here. What we mean by putting that bracket of an observable, some observable O, right? Which will be a function of the fields, right? So that observable is given to you. You can then find the expectation value of that observable, okay, through this ensemble averaging, right? So of course, I mean, this is your partition function, and here the partition function is there, but in addition, you are keeping the observable to take its average, right? This is a standard thing which you do in other places as well. The thing to note now is that this Lagrangian here, okay, this is now here because we have moved to something. So the E stands here for Euclidean, okay, Euclidean. And this happened the moment we did this. The T went to I tau, okay. So, okay. So then this Lagrangian, which we wrote here, we now say it's a Euclidean Lagrangian, right? So it is just that, the notation. And now you note that the Lagrangian actually, in terms of the
Hello, sir. Can I
yeah,
ask a question?
yeah. What is your name?
Yeah, my name is Prabhupada. Yeah.
Okay. Yeah. Go
What
ahead.
is what does it mean by t going to I tau? What is that limit actually? T.
So there is no limit actually. Yeah, I mean, by arrow here, I am just meaning that you are actually just replacing. Okay, wherever there is a t, you are replacing it by an I tau. It's just a substitution.
So this
there is
t
no
is
limit.
time.
Yeah, in
Time
the
good.
original thing, it is time, right?
Yeah, but
So
in the next slide, there is a integration limit 0 to beta. Here.
That's because this tau, here I have written that the tau ranges from 0 to beta. So in the Euclidean thing formulation, you not only introduce tau, now this tau can only be having a finite range, unlike this t here. Okay, so this tau has a range 0 to beta. and that's where the temperature is there. So it is very important, this range.
So
Otherwise, this whole thing doesn't know at what temperature it is, right?
so this tau
Yeah.
has a dimension of temperature inverse, because it is
Right,
going to.
right,
So if
right.
so, how it will, how t is the time dimension of time, and it is
Oh,
going to
this
I
is
tau.
yeah, but I mean, this is your these natural units, right? In the natural units, you can see the consistency.
Okay, okay,
Okay,
okay, but I don't
you should do that.
understand
Yeah,
the meaning. Means,
yeah. I didn't explain this prescription. That there, of course, you don't because I didn't even expanded on this prescription. So I'm just giving it like an information. So don't worry if you don't under. It's just like information you can take. Okay.
okay,
But I mean, there I can put some standard reference in the end. So if you are interested, you can further look it up for it. Okay.
okay, thank you.
But this is indeed a remarkable thing, right? There is this correspondence between statistical mechanics and quantum field theory, which is very important. So, um, right. So we are taking this ensemble average of this observable. And so that's how we take it. So, okay, so what I was telling is now to note next thing is that this Lagrangian here, right? You see um, there the gluon fields, okay? This field tensor looks like quadratic, right? But you see here, up if it was only this much, it would have been okay. It would still be quadratic in the gauge fields themselves. But here you see there is this coupling term, right, which involves these two gluon fields here, right, two gauge fields here. So now when you insert this expression here and write it out, you have terms which are no more quadratic in the gauge fields, right? There are higher order terms in the gluon field. Okay, so and that is problematic. Okay, but for the fermions, okay, still you see the fermions. This is a bilinear here, as well as this term here is still a bilinear. Okay, so if you have in your quantum field theory 1 course, and in this path integral approach, if you have done, it's a standard thing that if you have in this Lagrangian quadratic up to quadratic fields, those you can just analytically integrate. This integration then you can do analytically for those fields. Okay, it's like a Gaussian integration. So that can be done, which is written here. The QCD Lagrangian being bilinear in the quark fields allow for an analytical evolution of this expression for the integration over the psi and psi bar fields. Okay, so that can be done. And once you do that, finally you end up with this expression for the expectation value of the operator. Okay, so now this is written like this. So earlier it was this, right? But now the psi and psi bar, I think somehow they've been taken care of. So finally you have this expression. And what you have, so the integration over the fermionic fields, they basically give rise to this, what is known as the fermionic determinant term. Okay, and you are still left with now this Lagrangian, which is just A now, okay, instead of psi and psi bar, because those fields have been integrated out. So now in the Lagrangian, only the gluon part is left. However, you now have an additional determinant term. Okay. So far, these results are exact. And in LQCD, so in lattice QCD, what is done is this path integral is evaluated numerically, okay? Because now you cannot do the integration over these gauge fields any further analytically. So numerically, and of course, this integrations are over continuum variables, but if you have to do them numerically, you cannot do it simply over a continuum variable. So you have to discretize this space and time. Okay, so that refers to this lattice in this lattice QCD. So you discretize space time, and then put this whole thing on those individual lattice space-time points, right? So usually you will see when lattice results are quoted, there will be something like an n tau, ns, right? So basically n tau is giving you how many lattice points you are taking in this temporal direction, which is now is not the temporal like time, but this is basically the in some way the temperature direction, right? If the so 0 to 1 by t it varies, right? And then other side it is so this is n tau points you are taking, and then here the spatial thing you are dividing into ns number of points, and so altogether you will have a lattice with, suppose all your x y z the spatial directions you have ns points, so you will have ns cube times n tau, right? So that's your lattice points. Of course, the more number of points you take, that's a very trivial way of thinking the results will improve, but that becomes numerically more and more challenging. And so the whole idea is how within a reasonable with a reasonable lattice points, how you can intelligently come up with algorithms so that you can really evolve this, evaluate this, and get the QCD medium properties. Okay, so this now so far so good. However, so there is a slight problem here, and which is the following. So this method works well as long as this fermionic determinant, okay, is positive, right? Which is the case for zero baryon chemical potential mu b. Okay, so of course this integration is usually done, okay, using a something called a metropolis algorithm, right? So where you are basically uh, sampling different field configurations, okay, of gauge and fermionic fields, and then you are evaluating the weight factor of that configuration, right? So then this method can work only when those weight factors are positive, right? Then you can say, okay, this is more preferable than that, and then those information can get into this averaging and give you this value. But so this is ensured as long as the baryon chemical potential mu b is 0. Okay, till such time this fermionic determinant is positive and you work with a positive weight factor, and you can do this. However, at non-zero mu b, okay, non-zero mu b means you have a finite non-zero net baryon density in your firewall, right? And which is very easy for us to have, right? As soon as we do beam energy scan, we come to from LHC, we come to RIC, we start getting proton, which is more than antiproton, right? So there is a uh, net proton in your system, right? Net lambda in your system, right? Which for QCD, it means that there is a net baryon in your system, okay? Because of baryon stopping, which itself is poorly understood. However, I mean, whether poorly understood or not, the fact is that your firewall does have a net baryon density. So you need to understand the thermodynamic properties of QCD medium carrying non-zero net baryon density, right? So this is this is very much required for us, right? This is a condition which we see all the time. But at such non-zero mu v, what happens is there is this sign problem, which you will often hear people saying, and the sign problem is that then this determinant becomes complex. Okay, and once it becomes complex, there are various technical issues that come up, and then this program, okay, of doing a metropolis integration with a metropolis algorithm has this as a stumbling block. Of course, in the last 10, 20 years, there has been a lot of progress in the community, in the lattice QCD community, and we now have various groups have different methods to circumvent such a sign problem. and come up with estimates at non-zero baryon density. Okay, so that's the kind of status there. So
Excuse me, sir.
yeah,
Sir, can you again explain that sign problem? What is sign problem? I didn't understand it.
okay, you are Rakesh, right?
Yes, sir.
Yeah. Okay, so sign problem, I mean, I'm not giving you much details. I'm just telling this as like an information. So what you see is that these so this integration, okay, here is done numerically.
Okay.
Yes.
Okay. Yeah, so there was this question on the sign problem. I don't know how much you heard. Yeah, so maybe I can just tell in short that this integration over the field configurations, right? When you do, did you was I audible when I gave this mean x average? Hello, Rakesh?
Yeah,
No.
yes, sir. Now
Just
you are audible.
okay. So yeah. So what I'm saying is, suppose I mean you just want to compute some average x, right? So then basically what you do, you multiply that x with a weight factor f of x, right? So that f of x tells you how much importance you should give to a given value of x, right? So similarly here, when a given to a given gauge field configuration, how much weight we should attach to it, that consists of this determinant, right? So it is very important that it is positive. Otherwise, this one doesn't make sense, right? So that's the sign problem, that it is ensured to be positive only for zero baryon chemical potential. Okay, when you have non-zero mu b, this fermionic determinant can be uh, not positive. Okay, and hence it is of the wrong sign, which we say as a sign problem.
Okay, sir. I got
Yeah.
it.
Okay. Good. So so finally, now that we know how such expectation values can be computed um, on the lattice, um, so you now have these standard thermodynamic functions like the pressure, energy density, number density, okay, and so on. This is some conserved number density, okay. So you could compute these. These are your standard statmic expressions. You now know the partition functions, and so you can compute all these thermodynamic quantities. And one approach which is often used and which has been quite successful in tackling this sign problem is by incorporating Taylor expansion, right, around the zero chemical potential, right? So the pressure at non-zero chemical potential, you can expand it, okay, about the pressure at zero chemical potential, okay, in such a Taylor expansion way, right? So these quantities, then these Taylor coefficients, right, these are what are known as susceptibilities, right? And they are basically different order susceptibilities are different order derivatives of your suitably scaled pressure, right? Okay, so so this is some very recent results from lattice QCD, okay, with such a framework, how these thermodynamic quantities are computed. These results are for zero baryon chemical potential, but using such Taylor expansion techniques, uh, now there are also results available for non-zero baryon chemical potential as well. which also we will discuss in a while. So here, what is plotted, shown here, you see, is this quantity, which is the E minus 3p, right? So very often in the lattice community, they just compute this quantity, and then from here, all the others can follow through algebraic manipulations, right? Because you see, at zero chemical potential, you have only one parameter, which is temperature. So if you know one thermodynamic quantity, in principle, you should be able to compute or estimate the others, right? So what we see here is the x-axis is the temperature axis, right? And this, maybe you can refer to this right-hand plot because the left hand is a bit busy. And what maybe for specificness, let's look at this pressure here, okay? And what we see is that at low temperatures, okay, it has some smaller values, and then there is a temperature range, okay? What is the exact value of that range? We will come very soon, where these small quantities start rising, okay? And they keep on rising. The rise is quite fast, and then again the rise slows down. And but although there is a steady rise, however, so this is the non-interacting limit, which we discuss here. What is important to note is that even at temperatures like 400 MeV or so, which is here, there is still the pressure or other thermodynamic quantities, right? They are all quite different still from the non-interaction limit, which is signifying that there are still remnant interactions between the degrees of freedom, relevant degrees of freedom, right? Whatever they are. So, of course, this transition that is happening, right? It is of some value, and then there is a rise to another value. This basically is signifying the fact that the relevant degrees of freedom that are in that medium, right? They have their properties have drastically changed, right? From this side of the temperature range to this side of the temperature range, right? Usually, when we study and we see such a very drastic, I mean, when we see a change in the degrees of properties of the degrees of freedom, we study them in the context of phase transitions, right? But here, what is important to note is, although there is this transition, it is always smooth and continuous, right? There is no discrete jump. You see, at every temperature, it is smoothly rising. It is changing, but it's a smooth change, right? So in that sense, one cannot claim this to be a true phase transition, right? If you are asked what is one temperature where the degrees of freedom has changed, you cannot identify one, right? It will depend on what observable you are using to analyze the phase diagram, right? The result will, in principle, will depend on that. It may not, but in principle, it can depend on that, right? Okay, so these are some of the thermodynamic quantities at zero baryon density. These are equilibrium QCD medium properties, right? How much they can represent honestly or faithfully the medium property that is the medium that is produced in a heavy ion collision experiment, that's again a separate discussion, right? That comes next. But first, we should understand what is simplest to understand, right? Just the simple equilibrium QCD property. Okay. How much time do we have, Siddharth?
So almost we are done. So if you find a logical end, then we can stop here, or maybe so, 5 minutes if you want.
Okay. So then maybe I will I will then maybe just stop here in this slide, one more slide, because I will then just discuss this non-interacting limit. And then we can continue from here in the next class. So this high temperature limit, this line that is shown, this is very often you will see in lattice results or any paper on QCD thermodynamics. These kind of results are shown. You see there are two lines that are shown. In the high temperature, there is this line that is shown, and in the low temperature, there is this HRG results, these solid lines that have been shown here, right? And what the lattice results are indicating that below a certain temperature, say below 150 or 140, depending on what exactly you are looking at, there is a very good agreement between these lattice results and a simple model like HRG, okay? So that is one thing to note. In HRG, which we come here, we discuss, it's basically a gas of non-interacting hadrons, right? Now the hadrons are of course colorless objects, right? So the hadrons are, the quarks and gluons are bound inside these hadrons, right? So that's our hadron. So that's the basically the change in the degrees of freedom that we were just discussing. So on this side, you have these colorless hadrons, right? And on whereas and the lattice results are saying that this medium is trying to go towards somewhere here. I mean, at a very high temperature, these are expected to go to this non-interacting gas of quarks and gluons limit, right? Okay, so this so at high enough temperatures, right? So by high enough means where you can neglect the masses of the quarks, of the relevant quarks that you want to, that you are studying, right? For example, from the point of view of heavy ion collision, up, down, and strange flavors are good enough, right? Typically, whatever observables we have found, and if we want to understand them in some model framework, we know we have some estimate, indirect estimate of what is the highest achievable temperature, for example, at RIC or at LHC. And those temperatures suggest that it is enough from to discuss the QCD medium produced in heavy ion collision. It is enough to just take up, down, and strange and forget the other heavier quarks. They are too heavy to be excited and to take part in thermodynamics. Okay, in other studies, they do take part. I mean, there are nice observables that you can build with heavier flavors, but not thermodynamics, not within thermodynamics. So, so if you are in temperatures which are large enough to mass of, say, up, down, strange quarks, right? So there you can massless QCD then becomes a good approximation, okay? And further, at such high temperature, the coupling constant, right, is also expected to be very small, and so becomes progressively smaller and smaller, and hence these quarks and gluons degrees of freedom you can think them to start becoming non-interacting. And so you can just go ahead and write down what should be just a gas, a massless gas of 3 flavors of quarks and gluons, okay? That is a very simple expression to write down. You just have to remember the fact that your gluons are bosons and your quarks are fermions. So the appropriate statistics you should apply, okay? For gluons, you should apply Bose-Einstein statistics. For gluons, for quarks, you should apply Fermi-Dirac statistics, and you can just compute these expressions for. Of course, you have to keep in mind the degeneracy counting, okay? Polarization, spin, and so on and so forth. If you do the counting correctly, you will come up with the correct factors of these 8 by 45, 7 by 60, and so on. So this is an exercise that I have given here, that I have given here the expression for the pressure, and similar simple expressions one can obtain for other thermodynamic quantities, right? Like energy density, entropy density, number density, speed of sound, and so on. So you can check this. Okay, so I will then stop here, and from the next class we can take up from here. Is there any question?
Hello, sir.
Yeah.
Yes, sir. So I just
So
had a
what
small,
is your name?
yeah, this is Priyanshi.
Priyanshi. Okay. Yeah. Tell.
So just a small question. So this transition that you were saying, it is smooth and continuous mostly. So uh, is this the transition that we talk about when we say there is a crossover between this?
Exactly.
Okay,
Yeah.
and if we, so this in this range we see that this diagram gives an indication of a crossover. So if this diagram is extended towards say lower temperature, so do we also see the first order transition, like any sudden transition that we can mark as first order?
Yeah. So I think what you meant was high baryon density, right?
Yeah, correct.
So
Yes.
low. Yeah. So yeah. So we will come to that. So of course there are. It depends with which model you are working. So according to the model with which you are working, you will get your own phase diagram. Now, in actual QCD, what is the actual phase diagram? Okay, what is going on at sufficiently large sufficiently small non-zero baryon density? I think right now there is a good consensus, at least in the lattice QCD community, that the transition remains to be smooth and continuous, and hence this dashed line you see here, right?
Mm.
It ranges up to some mu by t. Okay, so usually the high, as you go to non-zero mu b, they usually will say with by scaling with t. So as you go to large and large mu b by t, up to some range, people there is control in these Taylor expansion kind of studies, and they can confidently say that they don't see any first order or critical point or things like that. But beyond that, what is happening? There are many models, there are many insights. Many important people have had a lot of contributions, and I mean, it's still a guess, right? It's still open. Let's put it that way. That sounds exciting, right? Yeah.
Yeah.
So we have to find.
Yes, and just one another question. So this diagram that we see, this 2D, so this is only in the massless limit, right? Will this diagram change, or will this have another dimension for mass if we do not consider the massless limit?
Yeah, so that's a good question. So in fact, I discussed this thing. So it's not just massless. So massless, of course, they can do. But even for physical quark mass, uh, now we have results for physical quark mass. Okay, and this often this transition temperature that is quoted, 154 plus minus 9 MeV, this is indeed with physical quark mass. Okay,
Yes.
so it's not the massless QCD, which is um, a fantasy thing, but this is now reality. Yeah.
Okay.
So now the computers are strong enough, and also there is a lot of progress in algorithms that they can do these calculations. Yeah.
Okay. Okay. Thank you. Thank you.
Okay. Good. Thank you. Any other questions?